Data architecture has evolved a lot over the past few decades. We have made remarkable progress scaling the machines and to address the basic V's, namely volume, velocity, and variety of big data. We have been able to manage large volumes of diverse data types. We have been able to reliably transmit high velocity data and process data intensive workloads. However, our methods have limitations with regards to organizational complexity and scale. The first generation of data architecture is the data warehouse. Data warehousing architecture today is heavily influenced by the early concepts of facts and dimensions, which were formulated in the 1960s. In this architecture, data is extracted from many different operational databases and sources. It then undergoes through transformation, where it is transformed into universal schema, which is represented as a multidimensional and time-variant tabular format. Finally, data is loaded into warehouse tables. Data then is accessed through SQL-like queries, and most of the use cases are serving the data analysts for reporting and analytical visualization. In this architecture, there is increased cost of maintenance over time. As the number of ETL jobs increase, they become from hundreds to thousands. There are lots of jobs, tables, and reports that only a specialized group can understand and maintain. This heavily transformed data, when it is used to train the model, it misses some of the attributes of the original data, or it transforms the data in such a way that the final data in the data warehouse has a different encoding and meaning altogether. Hence, data scientists and machine learning engineers prefer access to the raw data, which are close to the reality and which are also close to the operational systems. So, unlike data warehousing, the second generation of data architecture, which is the data lake architecture, attempts to retain the data close to its original form with minimum transformation. And it does contain transformation pipelines which are at the edge of the lake. Data scientists mainly access the lake storage for analytical and machine learning model training. And downstream from the lake, there is lakeshore marts created as fit for purpose data marts. And there is also feature stores which are created as fit for purpose machine learning training. But data lake architecture also suffers from complexity. It creates very complex pipelines of batch or streaming jobs, which is operated by a central team of hyper-specialized data engineers. It creates lots of unmanaged data sets with unclear ownership, which is often untrusted and inaccessible, hence providing very little value. Also, the data lineage and dependencies are very hard to track. The third and the latest generation of data architecture is more or less similar to the previous generations. However, there are a few modern variations, like there is support for near real-time data availability with architectures like Lambda or Kappa. There is attempt to unify the batch and streaming processing for data transformation with frameworks such as Apache Beam or Spark structured streaming, as well as a Spark structured SQL. It fully embraces the cloud-based managed services with isolated compute and storage. The new architecture also tries to converge the warehouse and lake into one technology, either by extending the data warehouse to include machine learning training, for example, the Google BigQuery ML, or alternatively, it builds data warehouse integrity, transactionality, and querying systems into the data lake solutions itself, something like Databricks Lakehouse. If we see the analytical data architecture, which has gone through evolutionary improvements, just now we looked into the last 3 generations, we also conclude that the technology and the products supporting these architectures have gone through a massive explosion. We have plethora of options for provisioning and handling infrastructure, generating analytics, enterprise applications, cross-infrastructure analytics, open source solutions for querying data, streaming, logging, etc. Data sources and APIs in health, IoT, and so on, and data resources like data services. There are a bunch of unchallenged assumptions of all the 3 data architectures, which we are going to look next.